Optimization, one of the big things that we're trying to focus on this year. The biggest problem is we're a space game, right? We have a lot, and I mean a lot of entities. Too many to count, and I'm sure someone will put a number somewhere. The more entities you have, sometimes they need to do some complex logic, and they may have to update to add a timer, check a timer, do something to continue the game going forward. And if you have a lot of these, it could be a very problematic thing if everyone has to update these every frame. If there's 5,000 things, that's 5,000 things someone has to do before the next frame could occur.
From a bird-eye view, a video game is a visualization of a simulated virtual world, constructed out of a basic update loop consisting out of a few simple steps. Sample input. External inputs are examined at the beginning of the frame so that the game can react to those. Such input can be keyboard, mouse, controller input, but other network data in case of a multiplayer game. Update world state. The virtual world has a state. Such a state is a multitude of things, like the kind of objects which exist, their position, their color, player health values, and so on. This state can change over time. For example, an AI can walk from point A to point B. During this step, such changes over time are computed. Lastly, render scene. The last step during each frame is the rendering. Here it is determined what is visible to allow the player a look into the simulated virtual world. Objects which are determined to be visible are then drawn on the display. We will focus on the update simulation and render scene steps, as those are the performance critical ones. Without going into too much detail, it can be said that each of those steps requires a fixed amount of operations, mathematical or logical, to update the world state and refresh the displayed image. If all those operations can be done within 1/60th of a second, also within 60 milliseconds, we will do the whole update loop 60 times each second, resulting in 60 FPS, or frames per second. But if those operations take 50 milliseconds, the game will refresh the scene only 20 times a second, resulting in 20 FPS. The whole point of performance optimization is to find ways to reduce the fixed amount of operations to be able to execute them within the target frame rate on the target hardware. To better explain what performance optimization consists of in modern games, the previous mental model of the basic update loop must be extended by some more details. While the upcoming explanation will still omit many parts, it will give a more accurate explanation of the interaction of various hardware components like the CPU and GPU. To go back to the initial example, a single frame looks like this. Here we use an imaginary execution unit which does all the processing for the world update and the scene rendering. The input sampling is omitted as it generally doesn't affect performance. But nowadays, practically each computer has a chip specifically developed for rendering, the GPU. Thus the work is normally split between the CPU and GPU. It is immediately clear that such a setup is not very resource efficient. The GPU and CPU are running in lockstep, and only one of the two chips is actively doing computations at a time. We can improve the situation by letting the GPU work on one frame while the CPU updates the simulation of the next frame in parallel. This pattern is called pipelining and appears everywhere when working with computers. For example, when watching online videos, the next few frames are downloaded, while the already downloaded frames are processed and displayed in parallel. But pipelining doesn't come without implications. When the CPU produces the data faster than the GPU can process it, the GPU will lag more and more behind. This lagging behind will be perceived as additional latency. On top, we need to store the CPU computed state somewhere in memory, while the GPU is not ready to process it. And as no device has infinite memory, we need to stop the CPU at some point and allow the GPU to catch up, as we cannot store more state forever. Here we speak of the CPU being blocked, waiting for the GPU. For Star Citizen, we generally opt for better latency and only allows the GPU to lag behind up to one frame. The same problem can happen the different way around. If the consumer is processing the data faster than the producer, which is called starvation. In general, one component will always be slower than all other components, which implies that the game will always be bound by something, here CPU or GPU. Thus, the first goal of performance optimization is to identify by which components the performance is bound, as the frame rate won't be affected if you optimize GPU performance while the GPU is already starving. This approach is also called critical path analysis, as it helps to identify the path which dominates the performance. A similar complex situation emerged on multi-threading CPUs, where each CPU now has multiple execution units, which we will refer to as hardware threads. To cope with this, strategies needed to be found to distribute the operations over the different hardware threads. The obvious choice is to use the same pipelining approach as with GPUs, but that has two large drawbacks on CPUs. Work balancing. As shown in the GPU-CPU example, the system will always be bound by the slowest component. To pipeline the CPU work, we would need to find chunks of work which are logical together and always takes the same time. This in itself is very hard to impossible in a dynamic game, and with the increasing number of hardware threads, CPU cores, we would soon run out of systems to put beside each other. We would also need a specific setup for each different CPU core count, resulting in a maintenance nightmare. Which is why our chosen approach is to batch the operations and to utilize the inherent parallelization found in video games. For example, there's rarely only one single character to update, so we can put each different character onto a different CPU core. The same happens with any kind of objects which we have. This pattern allows us to scale more flexible with the CPU cores. The process to change all the game logic is ongoing, and we are moving more and more parts of the game logic over to this approach to utilize more CPU cores more frequently and improve our performance. Input latency. The rules 30 vs 60 FPS discussion in the context of games is not only about how quick a frame refreshes and its visual quality. It is also about input latency. Input latency is normally measured in frames, as each frame needs a fixed amount of operations, regardless of the underlying hardware. So if we need 3 frames from user input till we display an effect, the input will have an input latency of 3 times 60 milliseconds, resulting in a 48 millisecond latency when running with 60 FPS. If our game runs with 30 FPS, which means a frame duration of 33 milliseconds, it will have an input latency of 99 milliseconds, nearly doubling the time between input and the visual reaction, resulting in a less fluent impression of the game. Adding more pipelining here would only increase the perceived latency, which is why we try to not depend on pipelining for performance on the CPU, even if it would result in a better frame rate, as it will cost us a worse and not really acceptable input lag.
One of the questions we get asked quite a lot is with our server having a target frame rate of 30 frames a second and clients having a target frame rate of 60 frames a second. How is that possible? Why aren't they tied together? And the reason for that is that we're not operating in something called lockstep, and lockstep would be where the server sends an update and the client has to wait until it receives an update before it goes, okay, this is where this entity should be, and then has to wait for another update and goes, right, entities move to here, and so on. What we actually do is the server will send its updates at 30 frames a second, the client's running at 60 frames a second. In theory, the client should receive an update for entities every 2 frames. So it has to kind of guess what's happened in the middle frame. So basically what it's doing is it's locally simulating all the entities. So an entity moving across a flat plane at a fixed speed and a fixed direction, it can guess where the entity should be at each point, and it'll get the next update from the server and go, that's slightly out from where it should be, I need to nudge that one a little bit over to the left. And a bit later down the line, I go, oh, the entity's turned a bit, so I need to nudge it a little bit over the other way. So that allows the client and the server to run at different frame rates, and we don't have to worry about doing something like operating in lockstep or anything like that, which can cause big issues because of latency on the internet and how that varies quite randomly all the time. It would be quite a bad experience. It's all right for things like turn-based games, but for something like a live action game like we're trying to do, it's just not going to work.
Reducing the amount of operations can be achieved in multiple ways. Which one is used is mostly depending on the current situation, time to implement it, and so on. Most often multiple approaches are also combined. Detecting objects too far away to be observed by the player. Here we need to decide after which distance we want to disable objects, what to do at the gray area when objects are barely visible, how to make it look like objects moved while the player wasn't looking at it, and various other corner cases. Let us assume a system where we need to keep track of 1000 objects in a single list. If we delete such an object, we must remove it from our list. The straightforward approach is to check each entry in our list for our object. When we found it, we remove the object. Afterwards, we copy each following object in the slot before it, to fill up the hole from removing the object. This will always require 1000 operations. Such an approach can work well for a small list, but if the list is large, or if we remove objects very frequently, it will take a good chunk of our precious operation budget. Thus, we need a smarter solution. Inside each object, we will remember the position inside our list. When we now remove an object, we immediately know its position. Then we can take the last element in the list, place it into the hole, and update its reference to the moved object. With this, we are down to 4 operations from 1000, which is a nice performance gain. But we also changed the behavior, as we now reorder objects in our list. Such redone can be okay or not, depending on how the objects in the list are used. This was only one example of an optimization of a very small part of the Boole game. In general, the Boole optimization process is iteratively finding where the game is bound, CPU, GPU, or which CPU's wet batch, and come up with a better solution to use less operations for the most expensive sections.
There are many moving pieces to this puzzle. Generally, the tech content or tech art people will be focused on the GPU side of the thing, the number of draw calls. We have about a budget of about 2,500 draw calls for all ships on screen at one time. And a ship can be anywhere between 500 draw calls to 800 draw calls at its highest resolution. So we try to optimize that as best we can. We have a few tricks in our bag to do that. One of the things is LODs. We have artists creating level of detail meshes, which reduce the number of polygons and reduce the materials as you go into the distance. These are being hand done and also generated by our Simplygon tool. We're also reducing the damage we're doing or reworking some damage on old legacy model ships, say like the Mustang. When you blow up a ship, you have all these little pieces of debris that used to be hand modeled. Now we actually just break the ship hull in half and change the shader, so you see some what we call UV2 damage. This reduces the number of debris items and therefore reduces the number of draw calls quite a bit. Draw calls are like the material passes on a mesh. So we're really, one of the other ways we can reduce draw calls is by combining meshes together in what is a process called skinning. And as I work on landing gear, I can take many pieces of the landing gear, pistons and gears and the feet, and combine them into one mesh, and I drive that all through a skeleton. So instead of 10 pieces with 10 draw calls each, you get one mesh with 10 draw calls. So really good significant savings there. Another trick that we do is with our viz areas and portal culling. So when we're on the outside of the ship, we don't want to draw the interior. And even when you're in another room in the ship, we don't want to draw the next room. You can think of portals as like a door. When it's open, it draws the inside of the room. When it's closed, it culls the room and the geometry out. We use our viz area portals to connect to the doors, which animate open and close, and then drive the portal to turn on and off. And like say the Caterpillar, those doors are skinned, so they're optimized, and they have portals on them. You will have noticed there are some issues with the portals recently, and we are working on about 4 or 5 major portal issues, but we will get them, and it will be faster and cleaner, and you can walk outside again and then see the exterior in space by standing on your deck. Another thing that's being worked on right now is called signed distance fields. And this is a technology that our Chris Rain is working on. It's a different way of describing a volume by recording these distances. So it stores distances, and what we've done to this point is use a volumetric approach where we have these voxels and we fill the ships with voxels, and this gives us our local physics grid. But when we move to a signed distance field, it'll be much faster. We can describe shapes in much higher resolution. And we'll know more immediately if you're inside the ship or outside the ship, colliding with the ship or not. This is going to open the door for new shield tech, new visual on the shield. So instead of a bubble that's kind of loosely shaped around the ship, you'll see a very tight shield that pushes just out from the plates of the ship. And also, one of the things we're excited about is of course, when we break the ships in half, the sign distance field is like a first step in getting us our multi-physics grids. So we'll be able to keep the interiors around and then allow you to reclaim and walk around in the ships after a battle. So you'll find new items and things that way.
Network code was a big performance bottleneck on the server, and the reason being that for the 24 clients that we were supporting in PU at the time, you had to gather all the information from the simulation, had to write it out 24 times to each different channel. And the way it would do this is, if you think about different threads, each CPU doing a different amount of work, you'd kind of have the main thread running along this way, going, right, there's a frame, and at each point in the frame, towards the end of the frame, it would go, right, now, network code, go off, do your thing, write some stuff out. And the network code on the other thread would go, okay, right, and start doing stuff. And as long as it had finished before the main thread started the next frame, everything was fine. But if the network code was running a bit slow, then it would stall the next frame on the main thread. It would cause that to wait until the network thread had finished. By the time 3.0 came out, we kind of, it came out with quite a few of the network changes that we've been planning. So we'd had the introduction of serialized variables. That's been in for quite a while. By the time 3.0 came out, pretty much all of the game code had been converted from using the old aspect and RMI systems to the replacements, which is serialized variables and remote methods. And what that meant for us is that we could focus our efforts on optimizing one particular code path, and we just leave the legacy system not performing as well as we'd like, but because not so much stuff is using it, it's not really an issue. The big kind of difference we made with serialized variables is that the fetch from the game, saying, okay, what's the state of everything? What's the things that have changed and we need to update? What's your current state, because I need to send that across the network? That was parallelized. So instead of the network thread doing all the work at a particular sync point with the main thread, it would just go, okay, how many threads have we got available? Okay, all of you, go and grab some data and send that to the network. And then the next part would be, okay, now we need to take that data and we need to send it off to each of the different channels so that they know that they need to do some work, and the channel being the network code's representation of a client. So then that was parallelized as well. And then the final part that we parallelized was okay, now we've actually, all the channels have got the data that they need to send, we need to actually go and send it. So that was parallelized as well. So we went from one thread doing all the work to splitting it over as many threads as we had available. So on the clients, we've kind of got the opposite situation where they're receiving all these updates from the server. It'll come in through the socket, it'll get processed by the network thread, and then there'll be a sync point with the main thread. It'll go, okay, right, network thread's ready, main thread's ready, here's all your data, this is what's being received from the server, right, go off and do your next bit of simulation. That part has always been pretty quick, to be honest. On clients, we're talking about roughly a millisecond to process all that data, even though it takes proportionally quite a lot longer to write the data and package it all up on the server. The unpacking of it's always been quite quick. So the network code itself has never been a performance issue for clients, because they're mostly just receiving data from the server, and what they actually send is so much smaller than what the server sends that it's never really been an issue for them at all. So bind culling's supposed to address this this mismatch between client and server, the sheer processing power that you have on servers and their ability to process everything, and the much smaller processing power that most clients will have. And the idea behind bind culling is that a client's only really interested in what's immediately around it. Anything that's on a different planet or a couple of 100 kilometers away and even out in space, there's no way you could reasonably see it, just shouldn't be there. And by that I literally mean that your client should not know about it at all. That would save all the processing of those entities on the client. It would save a bit of processing work on the server because it doesn't have to communicate information about those entities to your client. So it's definitely something we want to do. It's not a particularly easy thing to do. You need a way of controlling the updates on the server so that it's only updating not all the entities it knows about, but it's only updating the ones that it knows are in range of any player at all. So the ones that no player can see just don't update, and it saves processing time on the server. We've had to change assumptions on the networking code side, where previously it would say, okay, I've got an entity, it's a networked entity. Every client needs to know about this. And there would be assumptions all the way through the network code that relied on that being true. So we've got to change all those. So it's a bit by bit process that we've kind of unraveled stuff and added new stuff and optimized stuff that would allow bind culling to be possible. And we're almost there. The steps that are left are really, if you imagine the situation that you've got bind culling in and entities that aren't immediately around your clients don't exist, what happens when you fly to a different location? So you quantum travel to a different planet. You need all those entities to be there, so they have to be spawned. So the server's got to tell you about those entities. Information comes over the network, and then your client has to go and create them. Up until now, all the entity spawning has been synchronous, or what we call blocking, which means that the point in the code where it says, right, I need this entity, it'll basically stop whatever it's doing. It'll go and load the data in for that entity, create the entity itself, register it with physics and whatever else it needs to do, and then go, okay, this function can exit, let's carry on and do the rest of the game now. So we need asynchronous entity spawning, which is also known as object container streaming. And the idea being that a client will get a message from the server and go, okay, I need this entity, and it'll go off and go, okay, well, what files does this entity need to load? What data does it need to load? So I'll go off and do that on the background thread. And I'll go, okay, I've finished loading them. Okay, now I can create the entity. And it's not stalled the processing of the game. It's not stalled your client at all while that's going on. You can continue to play. So obviously that takes a bit longer. So the trick is to try and make sure that you finish spawning entities by the time they actually appear. So you've got to kind of preemptively decide to spawn stuff. So we need this object container streaming. That's the technology that's going to allow us to do the streaming of entities in order to be able to make bind culling work. So what I really want to do is develop the bind culling technology, finish it off as early as possible, so that in-house we can be testing it and making sure that it works, finding all the problems that it's going to cause. Perhaps an example of that would be, say you've got a mission from a mission giver, Miles Eckhart, and you need to go and find Miles. Miles is sat in his bar in Levski, and you're on Port Olisar. So we need a little marker rendering on your client to show where Miles is, so you know where to head. But with bind culling, the Miles Eckhart entity won't be there. So what do we draw the marker on? So those kind of problems, we need to try and figure out ways to deal with it. There's a couple of different ways we could deal with that situation. But until we do, we can't really put bind culling in because it could break the gameplay. Probably won't see the full implementation of bind culling in until, as I say, we get object container streaming in. But for us internally, we need to get it as soon as possible so that we can move on with some of the other stuff that we're planning. So what we've kind of done, which is another thing, so I've mentioned bind culling, I've mentioned object container streaming. There's also serialized variable culling, which is because we can't do bind culling just yet, because we can't get it out into the hands of the backers. Serialized variable culling is what we can do. So the way that works is same sort of distance checks that we were doing before. And if an entity is too far away, clients, the server will just say, you know what, I'm not actually going to send you any updates for that entity. And what that will mean is that because the entity is not receiving any updates on the client can go, okay, well, I can put this entity to sleep. I don't need to do any CPU processing on it. You can just stay where it is. So you can get a lot of the performance gain that we'd hope to see from bind culling, from this serialized variable culling.
This is also why games are generally not very optimized during development. It is very clear that the faster version is more complex and has more state, even in this small example. And more complex code means more places where something can go wrong, resulting in a bug. Because of this, we always have to decide on the trade-off between production speed and performance. If we focus everything on performance, feature development will be slowed down a lot, including future features, as they need to be developed against a more complex code base. To make it even worse, we could optimize all this code just to later realize that this specific part was not really needed. Or we need to implement something else entirely as the feature was simply no fun. There is a famous quote, "Premature optimization is the root of all evil." In other words, we need the whole final system to correctly understand and analyze it to make meaningful performance optimizations. But so much for the theory. In the gritty reality, our game can already be played, and playing with 15 FPS is no fun. To help the code leads and production to decide which features or optimization should be focused on, we perform a performance analysis. Sometimes features need optimizations to work, or a feature is needed to implement an optimization, resulting in dependencies between developers, making the whole progress more complex. Other times, code changes are trickier than expected, or introduce too much risk shortly before a release, resulting in a trickle-down effect of delays for other optimization or features. We use a set of different tools for performance analysis. The very basic tool we are using is a classic sampling profiler. Such a profiler works by stopping the CPU at a fixed time interval and recording what the CPU was doing at that time. If a function needs a lot of operations, it will have a higher chance to be executed when the CPU is sampled, resulting in a higher sample count, which then indicates a high-cost function. One drawback of a sampling profiler is that it only shows the function where the time is spent, but no context of why the function was executed, on which CPU, in relation to what other code or high-level state of the game, like the number of active vehicles. For this, we mostly use an instrumented profiler, which shows the executed function at a lower granularity, but shows what CPU core was executing when. This profiler can also show us plots of certain performance values we are interested in. Those tools are very useful to analyze a specific situation, but Star Citizen is a different beast. We have up to 50 players and many more planned on a single shared server, which also executes a physics simulation. This means what any player is doing can affect the other players, either by making the server slow, causing it to run more operations, which can be observed indirectly as jumpy movements on the clients, wrapper bending, and so on. All effects of the server not sending updates frequently enough. When they need to replicate the server behavior.
We've also been looking at some of the telemetry frameworks that we use to actually help us visualize and track what the actual performance issues within the game, inside the code base, actually are. Some of the improvements we've done to the telemetry, for example, allow us to capture data automatically during our play tests. The data would automatically be captured when the frame rate drops below a certain threshold. So, for example, we can use this kind of auto capturing to make sure we grab moments where we see these nasty bugs occurring which cause big performance drops. We would then take this data on board, analyse it as a team, and then look to see where the problems were lying. The various problems could then be either addressed by some of the engineers on the performance team, or in certain cases we might actually find that the ownership of the issues in question would be from engineers on other teams. So in that case we'd have to coordinate with them to look at fixing up certain issues that might have cropped up in the play tests. It's currently quite early stages for the auto capturing with the new telemetry system, but the initial tests seem quite positive. So we're hoping for 3.1 that we see a lot of these nasty issues a lot sooner, and we're able to fix them up in plenty of time for the actual release. Some of the other things that we've looked at adding to track the performance are some auto tests. The auto tests would be run by a test build machine once per internal build that we do. These internal tests would be something like having an automated player walk around a busy area of the game, such as Levski, or it could be have the player spawn into a ship alongside 30 AI ships. These auto tests would track various frame rate statistics, allowing us to see as we go from build to build, is our performance improving? Have we accidentally pushed the performance back a bit? In which case these tests allow us to catch issues as they arise, and whilst they don't necessarily give a perfect measure of the performance that we're likely to see in the live environment, they can at least give us a good indication that we're moving in the right direction, rather than us putting in a lot of optimization code changes and not actually knowing whether the changes are having the desired effect. So for 3.0.1, there's really two good ways at the moment for us to gather data from which we can decide what needs optimizing code-wise. The two ways that we have at the moment are taking the auto captured data from the internal playtests we do with up to 50 internal QA and a handful of engineers participating. And the other way we would look to gather data to analyse to see what we can optimise is just by doing local tests at our own machines. When we run those, we can spin up a server, connect in a client. We can potentially connect in headless clients should we want. We can play the game fairly normally, but with the additional debug commands that are available to us, we can do things like jump outside OLSR, instantly put ourselves in a ship. We can spawn 50 AIs, so we quite quickly can put ourselves in a scenario that in the real releases would see the frame rate stressed more than just running around as a single player in OLSR playing on the otherwise empty server. With those different situations, I'd also tend to do things like spawn 50 AI, then move the player away to another location in the game that's far, far away from OLSR, because then in that situation we'd sort of expect really that the performance should be better, because there's now a bunch of vehicles on the server, but those vehicles are now so far away from the player's vehicle that we shouldn't need to update them on the client with the same level of detail that we previously did when we were sat right next to him in an OLSR. So we'd be running these various different scenarios locally, taking a look at the data, and by analysing it, we'd sort of look out for instances like that where we could get some clear gains by not updating things that didn't need to be updated. We could also take that data and look into things like what are the most expensive functions in the game, what are the functions that are being called most frequently, which functions take the longest to run, which functions do a lot of allocation and deallocation of memory. We could also look at functions that were coming from code that we didn't actually necessarily even need to run for various game modes, or code that had been there since we inherited the engine. So we were kind of looking at sort of ways to improve pre-existing code that we did need, but also often some of the biggest wins would be actually removing or refactoring older systems that we didn't need or didn't need to use in the ways that we were currently using them for PU.
For example, one of the issues that we've always had is being able to test the server with a full load of clients. So particularly now we've gone to 50 players per PU map. You can imagine the amount of manpower it takes, and the logistical nightmare of trying to organise 50 people in QA, or volunteer developers to try and play test the game for a couple of hours and fill the servers and get back performance data. And then it's if you ask, say you observe a slowdown while you're doing this test. If you want to ask someone what happened, you have to ask 50 people and you get 50 different answers. There's this kind of, it's quite difficult to set up the tests and in getting the quality of information back that you require. So we're working on these things we've got called headless clients, which are basically clients without players, little dumb robots that'll press the keys in random ways. There's no keyboard, it's just a program that runs, but it's virtual keyboard. It's just mashing the joystick and mashing the keyboard and wiggling the mouse. And it's smart enough that it can get out of bed and get into a ship and then just fly around, firing in random directions. And that generates enough load that we can kind of simulate roughly what we can expect a player might do. And previously the headless clients have only been run on developers' machines. To get enough headless clients to help fill a server, they're being migrated onto virtual machines running in the cloud. So they have to be spun up on demand, shut down. The other thing I mentioned was getting back better quality of information. So we've had telemetry in the game servers for a while now. We've had some telemetry from clients as well. It's been a bit of a fragmented approach into how that's been gathered. So we're working with the engine team and DevOps again to try and get a more unified approach, get richer information about what the performance is, where the bottlenecks are on each of the clients and the server, try and get more contextual information about what everyone was doing at each point in the game, so we could go, okay, there was performance dropped here, what was everyone doing? All right, that guy, Caterpillar, blew it up, lots of cargo. Okay, that's a problem.
Really, with a traditional game, you probably tend to find that the performance for the majority of the life cycle of the development would be actually pretty low, probably 15 frames a second or less. Whereas the issue we have as an early access title, if you like, is that we've got to get our features in, write our new code, write our new systems, but yet we have to get those systems performing in an optimal manner that allows people to play the game at a reasonable frame rate and enjoy it, rather than having the luxury of only testing the game internally for the majority of the development cycle, then knowing exactly what content we want in the game, knowing what works, and then being able to optimize that in the last few months of the project. So really we do have an extra overhead of sort of continual performance optimizations that we need to look at, but that's all part of the great challenge that we've got here, writing the code for what we all see as a massive groundbreaking title.
During development, there's never going to be a line that we're going to cross and performance is suddenly going to be fantastic. It's always going to be this incremental process of getting better, and occasionally we're going to get worse. So basically what's going to happen is, as new features come online, the first thing they're probably going to do, besides work, fingers crossed, is make performance a bit worse. And then once we've measured the impact, we're going to try and optimize it back up again to levels that everybody's kind of happy with. But development being the key thing, it's never going to get to that kind of 60 frames per second for everybody, because it's more important that we spend the time on actually developing the game, getting everything in, getting everything working. So the kind of optimizations that we're dealing with now, you know, there's a few small kind of micro optimizations making things go particularly fast, but it's kind of system level optimization. So yeah, we know we're going to need bind culling, we know we're going to need server meshing, we know we're going to need the entity component update scheduler, we know we're going to need object container streaming. So these kind of system level things, these pieces have to go in so that we can build the rest of the game. But that's the primary focus of putting them in. It's to give us the tech to build the rest of the game.
Yeah, I guess the biggest takeaway out of this is there's never one answer in optimization. There's billions. I mean, that's why we have those profile markers in there. We need to see what's going on and work towards generating a solution to beef up that part of the thread that's going slow. Maybe we have to turn off some updates in the, you know, that are out of range using serialized calling, or maybe we have to optimize the way that we're handling physics on the planet because this particular way takes a little bit longer. It's analyzing the data, figuring out where in the thread that we are having issues in, and then finding a solution that works for that and doesn't break the game. That's probably the biggest takeaway and the biggest challenge.